let me introduce myself. So my name is Charlie Catlett. I am here as a representative of me, not any organization I work for, but just so that you have some idea of who I am. Last summer, I elected to go half-time, so I'm half retired. And the half that's not retired is welcome, come on in. So I'm a senior computer scientist at a laboratory outside of Chicago called Argonne National Laboratory. That's funded primarily by the US Department of Energy. So we're a science laboratory, and so we look a lot like a university with lots of different departments, from chemistry to biology to physics and computer science. But we don't have students except in the summer. In the summer we have about 400 to 500 students that come through, so we do get to work with students. In addition to that, I have an appointment at the University of Chicago in an institute that I helped to create called the Mansueto Institute for Urban Innovation. And that reflects the work that I've been doing for the last 12 years or so, trying to apply computer science to understanding the challenges of living in and operating cities, sort of like you've heard of things like smart cities and that sort of thing. I started my career back in the early 80s. And my passion has been really since that time a couple of things. One, we call high performance computing or supercomputers. So I've been involved in the largest, the supercomputer is 1,000 times faster than what you might see in a college or university. So I've been working in that area, and as a computer scientist, that means interacting with people from different disciplines who want to use those big computers. A chemist that wants to do a molecular dynamics model, or a weather or climate person that wants to do a climate model. And then the other thing that I've been involved in since the mid-1980s is the early development and expansion of the internet, and that sort of bled into the early expansion of the World Wide Web. So I told somebody the other day, I feel like this lizard in the king's palace, where some really interesting things have happened down the hall from me and with my friends. About this talk, I hope the talk is informative, but I felt like it was at least as valuable to make sure that as I'm going out on the internet over the last 6 months preparing this talk and looking at materials on this or that, I have chosen about 60 or 70 papers and websites that I found to be helpful in explaining some of these concepts. And so I thought, well, if the talk is good, that's great, but I want to make sure that you have access to all of that source material so that if you're interested in a particular topic, you can go and look at that material. And so this is a QR code that will take you to a Google Doc with that. And somebody asked me earlier, can I download the slides from there? And the answer is no, but that's a good idea. So it's no today because it's not there, but I promise to put a link so you can download those slides later. In the app, you can look at the slides, but I also would encourage you, if you're going to give a talk on AI to people in your church or youth or what have you, I want you to feel free to use these materials. They're God's materials, so if you want to download the slides, please do. And there are lots of notes in the slides as well. You can download the PDF if you want the actual PowerPoint, right? Okay, and so the way that you'll know what I'm talking about in terms of the reference here is that in the bottom right, you'll see these brackets with numbers in them, and those numbers correspond to references in that bibliography, okay? Great, so we're going to sort of run through where does artificial intelligence come from and kind of what it is. Take maybe a sidetrack along the way, since a lot of this discussion about AI has brought to the fore what's the difference between an AI if they get more and more sophisticated and a human, and how do we think about that as believers. So I want to take a little bit of a turn into there. And fortunately, since I have prepared the talk, I've seen some really excellent talks on what it means to be a human. So I felt that was good because my slide wasn't completely wrong, but I also learned some more things that I'll try to throw in mostly from Paul Coulter's talk that he gave to the Science Network. And then there's some opportunities and challenges that come along with AI, especially some of the new things that have happened in the last 2 years or so. and then we'll talk about some policy and discussions. And then after that, we'll talk about anything that you want with respect to things that I did talk about or didn't talk about. So sound good? So let's dive into it. So AI, artificial intelligence, has been kind of gelled as a concept in about the mid-1950s with this group of people here, John McCarthy and Marvin Minsky and others that are considered the fathers of AI. They had this famous conference that kind of coined the term and tried to define what it meant. They relied on the work of many others. I have to say I'm very thrilled because one of the fathers of computing is John von Neumann. And I got to meet his great-grandson here at ELF, and I took a selfie with him. So when I get home, all my friends are going to go, wow, that's really cool. You met John von Neumann's great-grandson. We'll talk a little bit about Alan M. Turing, who's was a mathematician in the UK. And then these three gentlemen up here in 2018 won the Turing Award named after Alan Turing, which is the equivalent of the Nobel Prize in computer science. And they won that award because of their work in something called deep learning, which I hope to at least sort of unpack a little bit for you. This is not a scientific or mathematical or technical talk, but if you want offline to go into a little more detail, I'm happy to do that. But I've tried to keep it at a kind of conceptual level so that you can be better equipped as you think about AI and talk to your families and your friends and youth about AI when you go back to your homes. Geoffrey Hinton, you probably read, and I have a slide talking about his exit from Google because he was so concerned about this technology. And we'll talk a little bit about that too. I haven't talked to him, I've never met him, so I can't tell you exactly what he's thinking, but I can sort of talk about some of the things that he mentioned that were on his mind. Before that big conference in the mid-50s, Alan Turing wrote this 1950 paper in Psychology and Philosophy, this quarterly review, a scientific journal, posing the question whether machines can think. And at the time, machines were these electrical, mechanical devices, not like the computers we have today, but the same basic principle of zeros and ones was at play back then, and the principle that you need memory or storage in the computer, and how much storage you had and how fast you could process it would determine what you could do. And so he proposed this test that he called the imitation game that we've come to call it the Turing Test. And the Turing Test is that you have this person here, and behind a wall is a computer and another person. And within, say, 5 minutes of conversation through that wall, texting back and forth, they didn't text back then, but you know what I mean, typing back and forth, could this human determine which was the computer and which was the person? And that seemed like a real stretch goal, a really, outrageous sort of idea back in 1950. But Turing also said he felt that, he predicted that by about 2000, so 50 years from when he did the prediction, he thought we would probably have enough memory, about 1 billion units of memory. He was only off by a factor of 6, which is pretty good. 6 billion is what we had on the largest machines in 2000. But he also thought that a machine would pass the Turing test, a 5-minute conversation by then. And he wasn't too far off on that either. I would say we probably hit that mark around 2017 or so when, among other things that happened, Amazon with their device that you can talk to, they ran a contest, and the Czech Technical University in Prague won a $100,000 award, and they won that by having a 15-minute natural language conversation with a computer. So that qualifies, I think, as at least a Turing test. So he wasn't too far off on that either. He was talking about whether they can think or not. And of course, now we're thinking, okay, well, they can appear to think, but is there intelligence there? And so, we'll get into that. Before we do, I want to just pause a moment and give honor to our anyone here that's from Poland, to our local hosts. Turing is known for this. There's a movie called The Imitation Game, if you have seen it. Turing is known for building this machine that every day would take some encrypted text from the interception of radio signals from the Germans during World War II and try to guess what was the key or the daily password to this machine called the Enigma that they would type the message in here, and what would come out is an encrypted message that looks like just gibberish. So they had to figure out what was the key that went into this in order to decode those messages. So Turing built this big machine, but he was able to do that in large part because the Polish Cryptography Bureau, and this guy here, Martin, whose name I'm sorry I can't pronounce, it starts with an R, it's in the notes, but he and his colleagues in Warsaw had already been looking at the pre-war commercial version of this before the war started and had made some headway on something similar they called the cyclometer. So it's really neat as we're here in Russia, as we're here in Poland, it's really neat to just look at the cooperation between the Polish and the French and U.S. and the British people during World War II. So well done, local hosts. Thank you for that. So in about the mid-50s, one of the ways that the science community pursued artificial intelligence was to start with a very well-constrained problem, a board game like checkers or chess, or eventually Go. And that's a really nice approach for doing AI, especially in the early part of it. This is Arthur Samuel from IBM playing chess on television in about 1956 or so, checkers on television. This is me standing in front of our supercomputer in about 1994. And what we had done was given a team from MIT the entire weekend of this $30 million machine to play a chess tournament, which got us into some trouble from the chemists and the physicists who said, "What? You're taking the machine away for the weekend to play a game?" And we tried to explain that, no, this is computer science and it seems like a game, but that's really not the point. I think they came in third in that contest. So that's 1956, 1994. Then a couple years ago, 97 or so, a computer was able to beat the world's best Go player. And this graph here, you don't really need to understand the details, but just kind of look at this blue line right here. What they did was they took a AI model. We'll talk about that vocabulary in a moment, but an AI program, a model, and they made it so that it could play Go against itself. And with every game of Go that it played, its score or proficiency in Go rose. And so over a period of time, playing against itself, it played millions of games and became eventually better than the best human Go player. And at a cost of a couple $1 million, maybe $10 million or so. So board games were a good way to start. And then we eventually went to sort of ended up over here with these chatbots and other things. A little bit of vocabulary and concept, if you will. As when people talk about artificial intelligence, it's a sub-branch of research within computer science more generally. And within artificial intelligence are multiple branches where people are taking different aspects of AI, like the ability to process natural language or to recognize objects and scenes, expert system speech, etc. And machine learning, which is the use of artificial neural networks. I promised to define that one too. Machine learning has, in the last 20 years or so, become not just a branch of AI, but the basic toolkit that most every other part of AI has now adopted for their use. So that's why you hear people talk about AI and ML kind of interchangeably. And the rise of machine learning was something that happened in about the early 1990s. And I'm showing you this timeline here. And the way to think about this timeline, which goes back to about 1940 and ends in 2000, is that there was a period of time, if you just looked at the publications in the field, where publications were dominated by artificial neural network research. And then there was a period of time from the 60s until about 1990 where it was dominated by more explicit programming, where we say, if you see this, then do this, sort of logic and symbolic programming. And then something happened in the early 90s that machine learning and these artificial neural networks took off. And one of the things that happened at that point in time is we got much faster, much cheaper computers and finally reached this point where we could start to do the computations at the scale that was needed to build and tune and train these neural networks, which is an expensive thing to do. There's lots of computation involved. And you could do some toy experiments back here and thought experiments, but you couldn't really do much at a useful scale until about 1990. The only thing that was happening in this period of time really of consequence using neural networks was the post office adopted a very narrow and simple AI system that would recognize written characters, like in a zip code. And so in the 80s, they implemented a neural network capability to do the automated mail sorting. Well, between about 1998 and 1992, we who were in the high-performance computing world underwent this transformation, or the transformation was thrust upon us, and that is that microprocessors, which power everything that is related to consumer electronics, microprocessors throughout the 70s and 80s got smaller and cheaper and faster at such a high rate that the more expensive custom-built supercomputers finally were overtaken. There was a New York Times article that was called "The Attack of the Killer Micros," the microcomputers. And so at the Supercomputer Center where I was at, we had industry partnerships where companies like Amoco or Eli Lilly or Kodak were buying access to our computer, and if they wanted 1 hour of computing time, it was $1,000. That was in, let's say 1988. By 1992, the microprocessors were fast enough that companies like IBM and HP were selling these fast scientific workstations, and they were as fast, not exactly the same capability, or some differences between the two, but in that 4 or 5 years, the cost for that amount of computing dropped from $1,000 an hour to $10 an hour. So this was quite disruptive in the business, and it's one of the reasons that you see this use of machine learning and artificial neural networks take off at that point. Finally, we have enough computing power that we can do reasonably complex neural networks. So before I go into that, of course, you've seen the AI has been in your lives for the last 10 or 12 or 15 years in various places. You've got your phone, or you notice when you pull your phone up and point it, it draws boxes around faces. That's because there's a neural network that's running in your phone that is tuned and trained to recognize faces. That's all it does. And so it's been given thousands and thousands of pictures. It's been trained to recognize faces. It doesn't know that that's a Christmas ornament, that's a part of a tree. It just knows that's a face and that's not a face. So it draws that box around. Navigating in your car, that's a neural network that is doing a comparison of all the possible routes and choosing the one that works best. Natural language processing is happening as you're talking to your Siri or Alexa or whoever it is your assistant is. This is cool here. This is because the Apple Watch is so closely tethered to the iPhone. The Apple Watch has an application on it where I can tap the application and speak in one language, and then it sends that to my phone, which has a much faster processor, and it translates it into a second language and then speaks it out. So I can go, where's the bathroom, and hold that up to somebody, well, in a way that's not so rude as just that, hold it up to somebody and it will speak to them in their local language, and they can speak back to me, which I think is pretty incredible if you just kind of like think about life 30 years ago, that we can now do this kind of thing. Like Dick Tracy would be so jealous. There are two kinds of AI that have had even more profound, I think, impact on your lives and mine. And one is called a recommender algorithm. A recommender algorithm is what Facebook uses to determine what to put on your news feed. It's what Netflix uses to say, well, you might want to watch these next. It's what Amazon here is telling me that it thinks I might be interested in buying. Well, how is it doing that? let's just think about Amazon. Every time I go on Amazon, I search for something, that's a piece of data about my interests. Every time I look at something and look at a product, every time I buy a product, every time I rate that product, it's more and more information that gives an AI model that gets that as input, an idea of what that model can predict that I will be interested in buying next. So these models, these recommender models, are everywhere, and they've really had a profound effect on our society, as I'll talk later here. But just remember recommender models. And then the other are sometimes called text completion models or language models. And these are what are behind that when you're typing see you, and then before you can type later, a little suggestion comes up that says later or tomorrow or whatever. Or if you're in a search, on a search site and you start typing and it tries to complete your sentence. That's the language model that's saying, you know, I've seen those three words in that order before. I've seen that 787 million times. And the highest probability of the next word based on all that history is this one. And so it's predicting based on what it's seen before. That's how these large language models work. Like, has anyone not, does anyone not know generally what I mean when I say chat GPT? Good, okay, that's good. Or it's probably only like 2 people because you were too embarrassed to raise your hand. So ChatGPT is this website where you can type an instruction or some words in, and it will give you a response. ChatGPT, behind that website, is a large language model, and a very complex one, a very large one. ChatGPT that was released last November was using a large language model that cost about $10 million to train, to set up and to tune. The one that was released called GPT-4, and I think it was February, that one cost over $100 million to train because it was 6 times larger, and therefore the network that had to be tuned and trained had a lot more knobs and switches that needed to be turned, a lot more computation. So those two, these large language models are, this is their ancestor, this type text guessing type ahead. So I've used a couple of terms. I've used terms like deep learning and machine learning and training and tuning and size and computational speeds needed and all that stuff. So let's kind of just really just briefly unpack that here. When we say machine learning has been around, as you saw that graph, it's been a concept for 70 years or so. And that concept is you have a program, a computer program, and inside that program are these little routines, a program within a program, that are equivalent to or analogous to a neuron. And they do some function, some mathematical function based on the inputs from the neurons to their left, and information flows in and out from left to right. So in this network here, it's an artificially small neural network. There are 9 neurons, and then there are many connections between those neurons. When we say we're going to train the network, that means we're pushing data through and we're trying to determine whether the answer that we get at the outside, at the output, is correct or how far off it is. And then we adjust a setting on each of those lines. And we'll call that setting a parameter. So this one has a certain number of parameters in a few dozen, and GPT-4 has 1 trillion parameters. And your brain has 100 trillion parameters. And when you learn, it's reinforcing connections and changing those connections in your brain. And that's what's happening in training a neural network. It's taking these connections and reinforcing or not reinforcing them. So machine learning is relatively simple neural networks, and therefore what you have to do in order to use them is your input data has to be carefully curated and labeled, and lots of effort that needs to go into making that data ready so that this simple neural network can ingest the data. And this is an expensive process. The reason that you're always asked to do these CAPTCHAs to show you're not a robot. It does show you're not a robot, sort of, but it also gives them labels that they can use in training models, because you've just told them where's the fire hydrant or where's the crosswalk or what have you. So a little dual use happening there. Deep learning is something that was introduced, and the concepts were introduced by those 3 Turing Award guys in the 80s, but it was really introduced once we had even more computing power in about 2012 or 2010. And that means deep learning differs from machine learning in 2 ways, I'll say. One is a deeper network, which means more neurons and more parameters. And also, because of that, you don't have to do this kind of expensive data prep before you can train the model. So you can now just start pulling data in with minimal engineering of data, translation and formatting, and push tons and tons of data through that deep learning model. And it will, as part of these functional layers that are in there, it will sort the data and it will categorize data numerically and do other what seem like magical things that are built up from just these little mathematical things. So deep learning, bigger networks, harder to train in terms of the amount of computing power you have. And machine learning is its little brother that's smaller networks and more expensive to do. But this deep learning had a profound effect in a number of different areas important to machine learning. One of them, you remember that in that tree there was a vision line, right? So like to draw pictures around those faces, you had to have a neural network that could tell what was a face and what was not a face. And the group every year that had a contest to see whose object recognition is what it's called, whose machine learning model was better, had a test that was done every year, and then your entry was ranked by its percentage of error, where humans would have 5% error. If I give you 100 pictures, a human would get 5 of them wrong. The best machine learning algorithms were getting 25% wrong, and they were on track to probably reach human performance by about now. But deep learning got introduced in 2012, and it dropped from 25 to 15%. So they got 85% right, or if you think in terms of grades, you know, they were getting a flunking grade of 75% here, 85 are getting a B, and now they're down at 12 here, so they're getting a B plus, A minus, A plus. And just in a few years with deep learning, massive progress was made in computer vision. And similarly, you probably all heard the term protein folding, or maybe seen the article about this, was around 2017. What's important in biology, and I'm not a biologist, but I work with them. I don't play one on TV, but I do work with some. And you have the genetic code for a protein, and you want to know in real life, how does that genetic code fold itself up into a 3-dimensional structure like you see under a microscope? And that's based on how the chemistry and physics of that molecule or those molecules fold together. Before 2017, getting the 3-dimensional structure of a protein was 2 or 3 months of an expert and his or her team working in a laboratory doing experiments before they had a structure. When deep learning was used to do the same problem, that 2 or 3 months expert laboratory process became a 2 or 3 minute type it into the computer. So you can imagine if you speed something up from 3 to 4 months and very expensive to 3 to 4 minutes and very cheap, what impact that can have on life sciences and medicine. So this is like, these are some of the very exciting things about these technologies and AI. So why did Geoffrey Hinton, up here in the upper right, why did he leave Google and warn of danger ahead? Well, the first thing I'll say is that there are others who are equally prominent as Geoffrey Hinton who have not had the same sort of reaction. And so there's disagreement among experts on the dangers or the probability of different disaster scenarios coming out of AI. And just so you know, I was in the communication and media network earlier today, and they know, and I think you know too, that headlines are not designed to summarize the story. They're designed to get you to read the story. So headlines are always going to be scary, but before you get scared, read the story and then think about who wrote the story and why they wrote the story. But he thought that we were like 30 to 50 years away from something something that's a little bit more powerful than what we have now. He now thinks it's more like 3 to 10 years away to get to the point where you could pass a Turing test, in almost any topic in long conversations with more human-like intelligence. And he feels, as I think everyone does, that there needs to be some care as this is scaled up. And I'll just give you my opinion. I think it was a big mistake for the company OpenAI to release ChatGPT when they did, instead of doing the work they've done since then in making it safer and less toxic. And ChatGPT today is way safer than it was 6 months ago. And so a lot of this panic could have been lessened, I'll say, if they had not been driven by wanting to be there first and release this. But it was a surprise, and I had been, along with my other people I work with, I'd been playing around with GPT-2, the smaller previous version of GPT-3, which was released in November, and we'd been playing with that. We've been pretty impressed with its ability to create, to synthesize information. Then GPT-4 came out in like February, and we were as blown away as anybody else was. And so this kind of took the computing and AI world even by surprise. And without going into lots and lots of technical detail, one of the things happened, there's a theme that you'll hear here. Computing got faster and cheaper in the 90s, and so we adopted machine learning. Computing got even faster and even cheaper in 2010, 2012, and so we made bigger models and we did deep learning. And computing got faster and bigger again 2 years ago, and so we could finally train models that were large enough to have capabilities that even we wouldn't have imagined that they could do. I wouldn't have imagined that a large language model, from what I knew about GPT-3 a year ago, would be able to write me a children's book in the Dr. Seuss voice and style, or do some of the other things that these can do, or that it would be able to answer a question, but not just answer the question, but answer it from the perspective of a specific demographic, like, I want you to explain to me machine learning as if you're a biologist who's read a book on machine learning and I'm a 5-year-old. And it will actually give a reasonable response to that. That kind of complexity was unexpected with that kind of with the kind of scale that we've had. So what does it mean to be human? We had this. I think that we're at one end or the other of the spectrum if we have firm beliefs about it. And one end, many of the folks in tech and science, many of my friends and colleagues have this idea here that we're just this emergent, mysterious property that came about from natural forces and physics and chemistry. And we believe that we're creatures made in the image of the creator of reality, the image of God. And that's something that will run through everything from how we think about how humans are unique to what we think is the ultimate purpose of humans and of our lives, and what happens to us and where do we go after this body falls apart. And over the decades, there's been research into what makes humans different than other created things, like a lot of tests against different kinds of primates. And we used to think it's because we use tools, but it turns out they use tools also. We used to think it was because we use language, but it seems like they can use language too, maybe not as articulately as we can, and then have emotions. But anybody that's got a pet, especially a dog, knows that not only do they have emotions, but they have a sense of guilt. You've come home when your dog's done something bad, you can tell that dog feels guilty. At least they're sad. But nowadays they're thinking, and this I'll borrow some things I learned from Paul Coulter earlier this week. He talks about a number of things, including this theory of mind, which is an awareness that you're like me and that your thought process is similar to mine, and so I can sort of imagine what you're thinking and know that you can imagine what I'm thinking. And so that's a general form of empathy, but it helps us to cooperate. And so the current theory is that because we as humans can imagine what another person is thinking, we can cooperate in ways that apes and chimpanzees cannot. And there are a couple other things. One is we're the only species on the planet that blushes, so the notion of being embarrassed, which means, so why would I be embarrassed? Because I don't like what I think you think about me, right? So if I do something outrageous and you all go like this, I'm going to turn red because I know that you're thinking that this guy's weird, right? And what Paul said, what I thought was really interesting, is that humans have something like 7 layers of this. Like we can go, I know what you're thinking, and I know that you know that I know that you know that I know that you know what I'm thinking, right? And he postulates that 7 is the average, that women can do that like 8 times, but men are kind of like twice. I know what you're thinking, right? But women are like, I know what you know I know. So here we say, okay, well, whatever. And as Paul differentiated the functional differences from the purpose difference. Functionally, we have a different kind of life that was breathed into us than just biological life, the conscience and our consciousness and our soul. And that's what we believe. And the details may differ as to what we think about that, but we know that we're created in God's image and he breathed life into us, or at least into Adam and Eve and all of our other ancestors. And that's the biggest difference. We are created in the image of God. These primates were not. And then as far as like the purpose of people and where they're going to go, on the left-hand side, there's a school of thinking, a philosophy called long-termism that is quite pervasive in high technology and ultra-rich thinking in terms of the good of mankind or humankind, even if it's at the expense of people, individuals, or even societies. And where they think that we're going is from a biological human to an augmented biology, a biological human augmented with technology, to being able to be uploaded into some computer. And there are people that believe this, and that's what they view as the future. That's their hope. But our hope is promised to us by Jesus Christ, who proved that we should take this side instead of this side because he's the only person that's ever rose from the dead. So there's reason to believe him over here. And Ray Kurzweil is still alive, but he's not going to raise himself from the dead, nor have the other people who have died that have held that view. So there's a difference in our philosophy as well. There was a letter that came out a few months ago, was signed by a bunch of people that said we should stop all this for 6 months while we figure out regulation. Well, that came from this group called the Future of Life Institute at Oxford, and they are some of these long-termists. And it's an example of we have at least some alignment in the big picture goal that they talk about, like we want to act responsibly and not wipe out the human population, and so they do too. But we disagree on the difference between the value of humanity and the value of individual people. To them, humanity is this big blob of lives. The individuals don't matter so much. You kind of have that in the Chinese Communist Party. It's all about everyone, and your individual rights are not so much an issue of importance. And we, on the other hand, believe that every human being is infinitely valuable. So this leads this sort of semi-alignment of goals, but really fundamental differences in how we get there, leads to things like this, which are really quite amazing. That in writing, one of their co-founders has made statements like this in writing. There are others as well, where it seems inefficient to put money into poor countries. We want to put money into the countries most likely to come up with the technologies that will help us upload ourselves. Another one of their founders also said in my notes, and I didn't want to clutter the slide, also said in order to preserve humanity, so we can get to this, well, they actually call it the safe place. That's their version of heaven. In order to get there, we are probably going to need a government that's worldwide and that can surveil everyone so that we keep everything in check. So that's a kind of a different philosophy than we have as well. Although I'll say we do want one global government, don't we? It's just we disagree on who the king should be. Another case is we might disagree with a statement made, but we don't want to discount the thoughts that follow that statement. I was sent to this New York Times op-ed a few weeks ago from author named Yuval Harari, who says, among other things, in the beginning was the Word, and by that, and then he goes on and talks about the power of language. And we disagree with him about the origins of language and the word, and even what the word is, because we understand that God created language, and that's his vehicle for communicating with us and for us communicating to one another. And he's exactly right that this is super powerful. Language is very powerful. Can you think in the history of humankind, can you think of a single example where we had to interact with something using natural language like we do with ChatGPT, where there wasn't a person at the other end? Might have been a spiritual person like an angel or God, but we as humankind have never encountered anything that speaks to us with language that doesn't have intent and agency and other things. And so we're wired to assume that the thing talking to us with language is like us. That theory of mind we will project on it. And the ability to, when he says hack and manipulate the operating system, the underlying program that runs ourselves and our civilization, he's talking about the power of language. And this is at the heart of some of the concerns that we all have about AI that we'll want to talk about more in a moment. Just a word picture to think about these large language models so that we can keep in our minds that we're not talking to a being that has opinions and is like us. In 1980, John Searle, who was a philosophy professor at the University of California, Berkeley, came up with this idea of the Chinese room experiment. And in this experiment, you have somebody in a room who doesn't speak or read Chinese, and you have Chinese characters coming into the room, and over time, this is a very smart person, right? But over time, this person has this instruction book that gets built up about when you see these characters respond with this character, and pulls those out of its database of characters. So you can send these characters in, these characters, and it's seen something like this before, and so it knows that the next characters in the sequence are probably these, just like it's completing your text that you're typing. And so it happens that I use Google Translate, so this is where's the best coffee in Rome, and surprisingly, it came out with the correct answer, which is St. Eustachio's, which is near the Pantheon. So you'd think that whatever's behind this understands good coffee and has some knowledge of Rome, and maybe has some experience about how good the coffee is at St. Eustachio's. But it doesn't have any of those things, even though it answers in a very cogent and very correct way. It's just saying, well, based on these things here, the next one is. And large language models aren't dealing with letters and words. They translate those into numbers. It's all numbers. Yes? The question is, doesn't somebody have that knowledge in order to write the instruction book? And the answer with these large language models is no. They get that. The instruction book is built up by ingesting millions of pages of text and detecting patterns in that text. So no human has put knowledge into this, and these large language models are trained by millions and millions of pages of text. Some of the things that we need to kind of think about with AI, before we go to large language models, I want to come back to things that have been around for 10 years. You've heard the term echo chamber, and you've seen the polarization in society around social and political issues. And one of the reasons for that, I'm not saying it's the only reason, but one of the things that has deepened that divide among Christians even, not just people in general, are recommender systems. And the reason that I'm saying that is recommender systems are designed for very specific things. The recommender system in Facebook is designed so that it's rewarded, if you will, so it grades itself by how long it can keep you interacting with Facebook. And so it is experimenting with showing you different things. Not a person, but the algorithm is watching what you're looking at and saying, oh, they want more of that. If I give them more of that, they'll stay on the site longer. And it's kind of like this conveyor belt sushi restaurant. Imagine that it's just a sushi belt just for you. And what you take off of that and is telling whoever's putting stuff onto it, in this case, a dumb algorithm, that that's what you like, and it'll give you more of that. If you keep taking cheesecake and never take anything nutritious, the recommender system doesn't care. It doesn't know anything about nutrition. It just wants to keep you in the seat taking more stuff off the conveyor belt. So it doesn't require any sort of bad intentions on the part of a human. The natural outgrowth of a recommender system is to give you more of what you asked for or what it sees that you want. And this is one of the things that I think we need to take a step back when we're looking through news feeds or social media feeds and ask, if you read the previous page, I'm kind of getting upset about this. This is outrageous, I'm mad, et cetera, and maybe that's a sign that you should step back and go, okay, well, that's an outrageous headline. What does the article actually say, and who wrote that article, and what might they gain from me being upset? So I think we need to have a better warning system for misinformation than we have demonstrated in the last 10 years, because AI is going to make those things much more personally targeted and much more powerful. So these are dainty morsels, in the words of Proverbs, that we need to be careful about. The second thing is bias. This is some of my own work in crime prediction as an example of unintended bias. We took the database in Chicago for crimes, and then we looked over a period of years across the city, and based on the history of crime in this area or this area, 800 and something sub-areas of the city, we made a prediction that said we'll turn the area red if it's more likely than the other parts of the city to see a crime in the next, say, 34 hours, and green if it's less likely. Doesn't mean there will be a crime there, it's just more likely that a crime will happen there. And because I'm a computer scientist, not a social scientist or policy person, one of my colleagues who is a policy person said, wait, that's not the crime database. That's not all the crimes. That's all the crimes that the police found. Lots of crimes that the police didn't find. So this map is sort of like also where the cops are. And if we show the cops this map and they go to the red places, then we're not making anything any safer. We're just harassing the people in the red areas, and it's going to get redder because the cops are there. So without intending to, the input data, and this is what happens with large language models, you have to really understand what that data is if you're going to make an algorithm out of it. And other things have been done with algorithms and good intents, like in Pittsburgh, Pennsylvania, they had an algorithm that would help social workers to identify families that are likely to have child neglect as an issue. And that algorithm was, as you can read right there, it was biased based on the data that was there before, to the extent that the social workers who actually had experience on the ground with families were going, wait, this is way off. We don't agree with this algorithm. So as we put these algorithms in, and all these are known issues, and people that are working in this area are really trying to fix them. It's not like it's going out of control and we're putting these things everywhere, but it's what we have to do to make these things safer, if you will, to use that term. So the other thing I would say, this notion of emergent properties, we see these large language models like ChatGPT doing things that they shouldn't be able to do based on our understanding of those models. And we call those emergent because we didn't train them to do this, but they're doing it anyway. That's a really difficult judgment to make, in the same way that there's not agreement among people that study the functions of humans versus chimps. There's not agreement in how you interpret a particular example. And so when you ask the large language model to do something, have to be careful about not ascribing too much to it. So I'm going to give you an example of what I feel like is over-ascribing intelligence to GPT-4. This is the old one, GPT-3, draw a unicorn using this text-based language. So it spits out a program to draw a unicorn. You can see the difference between 3 and 4 is quite remarkable in the drawing of the unicorn. You can see over the course of a month that it was able to learn how to do it better as they put more training in. And then what I find suspect about this one part of the paper is they said, and we removed the horn And then we said to GPT-4, please replace the horn. And it did. So that means it has a notion of sight. It can see the unicorn. And I'm like, well, no, you took some lines of code out of the text and it found the lines of code that were different and put them back in. So that's a little bit of an oversimplification of what they did, but it just shows that when somebody says that this model can do this or has this level of intelligence, number one, if it's a headline, don't believe it. Number two, if it's in the text, ask who is it that's doing the test and do they know how to do these kind of tests and have they been rigorous in their research. I also thought it was interesting to try to compare this to the performance of a human. And this is my granddaughter Ellie, who's 5. And I think we would all agree that her unicorn is far superior to GPT-4. And GPT-4 did, and Ellie it has not cost $100 million to train Ellie to do unicorns. Another interesting result is that we also asked the 3-year-old to draw a unicorn, and it's not up there because the 3-year-old said no. So let me try to kind of wrap up with, not to go into lots and lots of detail, but to give you maybe kind of a framework to think about AI opportunities and concerns. And that is to kind of categorize them into 3 areas. And you can think of this as underlying technology. This is like, how do we extract iron from ore? And then this is like the blacksmith takes that iron and makes a hammer or a saw or something like that. And this is like some person, a farmer or a carpenter that uses that tool, right? So you can already see that there's things like, okay, well, I can make a machete, which is really good for harvesting bamboo. It's also good for hurting people, right? So every one of these has that kind of dual property. But I think it's helpful to think in these different categories. This is in the computer science world. These are some of the challenges that we're trying to solve. The one you've probably heard the most about is hallucinations, which means they're giving us information that's not true. It's just extrapolated, perhaps. We don't really know how or why it happens, but it's one of the reasons that we need to view this output with some suspicion. And so these are computer science problems. These are the methods that we use to take these large language models and turn them into tools. We need to be very vigilant about how that's done. And one is the provenance or the origin and the type of data that's used to train the model, because whatever biases are in that data will bias the model. Another is ethics, and we talked a little bit about that with this notion of this safety layer in ChatGPT that will make sure that what comes out is not crazy or biased, et cetera, to the extent that it's effective. And then where I think it hits us as individuals who are not working in AI is in the application, and this is where companies have to make decisions to use AI responsibly, and we don't have an assurance that companies will, and there's some track record from all companies that they don't always put ethics above, or I'll say societal benefit above the stock price and profit. So among the two, I'll just mention, of course, there's employment. We can talk about that. Deepfakes and disinformation. Imagine that already in the social media, based on your interests and what you've taken off of the sushi conveyor belt, you're getting news stories that are intended by their source to move you in some direction. Imagine now that that's not just for all people that are like you, but it's for you personally. And imagine it's written by a very articulate AI like GPT-4, and all of a sudden you've got an individual disinformation feed that's aimed at you. That's why I say, put some warning flags in. And then human AI interactions. I'm kind of concerned about this. You have an example here a few months ago of a man in Belgium that took his life. He got some advice from this chatbot about how he might do it. And the power of language is such that even though it says, please remember to always seek professional medical attention when considering any form of self-harm. Well, that was not an effective warning. And so maybe the lawyers for this company were like, well, we warned them, but the power of language is just, it's way beyond that. And then my son sent me a video that, as we were talking about this topic, he's a gamer. That's not him, but it could be him. And he sent me this video of some of these virtual worlds that people play the games in, and they've now started to put in these characters that are AI that you can interact with in real time, which is pretty cool. But you can also imagine that some of our youth and maybe adults would prefer to spend more time with these AIs than with other people. And I don't think that's our solution to the loneliness and the despair that our youth are experiencing, as we heard last night. So these are some things that I'm concerned about, and I'm going to skip through. There's some policy that are happening here. Some of these immediate risks, I think, are important to talk about. The possibility of social media getting even more powerful at manipulating, especially young people. And I went and read one of the papers that this article referenced, and found this research in that paper from the UK looking at 84,000 social media users of all ages. And one of the things they found is that youth between 11 and 16 are super vulnerable, and social media is one of the things that causes them to be, according to their reporting, less satisfied with their lives. And you can understand that I'm a 13-year-old and I know my life, and my life is nowhere near as good as that person on Instagram who's just posting pictures from their vacations and the highlights of their life. This is Eric Schmidt, who used to be the chairman of Google, and I find to be a sort of voice of reason in this area, has even some suggestions. With, you'll see reference number 52 at that QR code, at URL. There's a really nice statement of principles that comes from the Ethics and Religious Liberty Commission, which is part of the Southern Baptists. I'd never heard of them before last week, and a friend of mine gave me a link to this. But in each of these 12 areas, they give a paragraph about what we believe as evangelicals about medicine or relationships or bias, or et cetera. And then another paragraph that says, here's what we reject as an implementation of AI. Like in medicine, we believe that AI has the capability to make medicine better and cheaper and more available, but we reject the idea of using AI to augment our bodies that God created. And then in each one, there are a set of verses. And I just found this last words in this statement to be appropriate. We do not need to fear AI. We should be cautious. We should pay attention. But God is way more powerful than anything we could create. And AI is just another thing that we've created. So let's stop there and we'll take questions.